Hello everyone, welcome back to my channel. Today we're diving deep into a topic that affects us all, the global plastic waste crisis. It's a serious issue with far-reaching consequences, but fear not. Because we're not just highlighting the problem, we're exploring solutions, specifically the revolutionary concept of plastic to energy conversion. So buckle up and join us on this journey towards a cleaner, greener future. Part 1. Introduction. Let's start with a brief overview of the global plastic waste crisis. Did you know that we produce over 300 million tons of plastic every year? That's equivalent to the weight of the entire human population. And unfortunately, a significant portion of this ends up in our oceans and landfills. Now let's talk about the environmental impact of unmanaged plastic waste. Plastics can take hundreds of years to decompose, releasing harmful chemicals in the process. The consequences are devastating for both wildlife and humans. Our oceans are turning into plastic soup, endangering marine life. Birds and animals mistake plastic for food, leading to a chain reaction of ecological imbalances. It's a problem that affects us all, and we can't turn a blind eye to it. So, what's the solution? We need comprehensive plastic waste management strategies. Recycling alone isn't enough. We have to rethink how we produce, use, and dispose of plastic. It's time for a holistic approach. Communities, businesses, and governments all play a role. From reducing single-use plastics to investing in sustainable alternatives, we must work together to tackle this issue head-on. Enter the game-changer, plastic-to-energy conversion. Imagine turning plastic waste into a valuable resource. It's not just a dream, it's a reality. By converting plastic into energy, we're not only addressing waste, but also generating power sustainably. It's an innovative solution that has the potential to reshape our approach to plastic waste management. How does it work? Well, there are different methods of converting plastic into energy, such as pyrolysis, gasification, and incineration. Each method has its own advantages and disadvantages, but they all share the same principle, breaking down plastic into smaller molecules that can be used as fuel. By doing so, we're not only reducing the amount of plastic that ends up in landfills and oceans, but also creating a new source of renewable energy that can power our homes, vehicles, and industries. Sounds amazing, right? Well, it is, but it's not without challenges. Plastic to energy conversion is still an emerging technology that requires further research and development. It also faces regulatory and social barriers that need to be overcome. That's why we need your support. By spreading awareness about this topic and supporting initiatives that promote plastic to energy conversion, you can make a difference. You can be part of the solution. So, what are you waiting for? Join us in this mission to turn plastic waste into energy and create a better world for ourselves and future generations. If you enjoyed it, please like, share, and subscribe to our channel for more content like this. Part 2. Plastic waste, types, sources, and composition. Now, when it comes to plastic waste, it's not just one size fits all. Plastic comes in various forms and serves different purposes. We can classify plastic waste into several categories, such as single-use plastics, packaging materials, and industrial plastics. Each category has different sources, impacts, and solutions. Single-use plastics include items like straws, utensils, and bottles that are designed for one-time use. These plastics are often discarded after a short period of time, ending up in landfills or oceans. They pose a threat to wildlife, as animals can ingest or get entangled in them. Packaging plastics are everywhere, from the packaging around our food to the wrappers on products. They account for a large proportion of plastic waste, as they are usually not recycled or reused. They also contribute to greenhouse gas emissions, as they are made from fossil fuels. Industrial plastics are more heavy-duty. Used in manufacturing and construction, they have a longer lifespan than other plastics, but they are also harder to recycle or dispose of. They can leach toxic chemicals into the environment, affecting human health and ecosystems. Now that we've identified the types, let's talk about the major sources of plastic pollution. It's not just about what we use, it's also about how we dispose of it. The biggest contributors to plastic pollution are often related to our daily habits and industries. Think about it: discarded plastic items on our streets, plastic litter in our oceans, and industrial processes that generate plastic waste. All these contribute to the global plastic pollution crisis, affecting ecosystems and wildlife. Now, understanding the composition of different plastics is key to effective waste management. Plastics vary in their chemical makeup, making some more challenging to recycle than others. Each type of plastic has its own set of characteristics that determine how it can be processed. Ever notice those recycling symbols on plastic items? They indicate the type of plastic and help us understand how to manage them properly. For example, PET is commonly used in beverage bottles, while HDPE is often found in milk jugs and detergent bottles. Now let's talk about the recycling challenges we face with different plastics. While some plastics are easily recyclable, others pose significant challenges. Contamination, lack of proper recycling infrastructure, and the sheer variety of plastics all contribute to these challenges. Contamination occurs when different types of plastics are mixed, making it harder to recycle them efficiently. The lack of widespread recycling facilities and awareness further compounds the issue. It's a complex puzzle we need to solve to improve our recycling rates. One of the main challenges is to identify and separate the various kinds of plastics, which have different chemical properties and melting points. Some plastics, such as polyethylene terephthalate, PET, and high-density polyethylene, HDPE, are easier to recycle than others, such as polystyrene, PS, and polyvinyl chloride, PVC. Moreover, some plastics may contain additives or contaminants that affect their quality and safety. Therefore, it is essential to have accurate and reliable methods to sort and clean the plastic waste before processing it into new products. Another challenge is to increase the demand and supply of recycled plastics in the market. Currently, the production of virgin plastics is cheaper and more convenient than recycling, which discourages manufacturers and consumers from choosing the more sustainable option. To change this situation, we need to implement policies and incentives that promote the circular economy of plastics, such as extended producer responsibility, eco-design standards, green procurement, and consumer education. By doing so, we can reduce the environmental impact of plastic waste and create new opportunities for innovation and growth. As we wrap up this exploration into the types, sources, and composition of plastic waste, remember that our choices matter. Plastic is a versatile and durable material that has many benefits but also poses serious environmental challenges. We have learned about the different types of plastics and how they are classified by their resin identification codes. We have also learned about the sources of plastic waste and how they contribute to the global plastic pollution problem. Being aware of the types of plastics we use, understanding their sources, and supporting effective recycling are all steps towards a sustainable future. By choosing reusable or biodegradable alternatives, avoiding single-use or disposable items, and sorting our waste properly, we can reduce the amount of plastic that ends up in landfills or oceans. Part 3. Plastic waste collection and sorting techniques. In this video, we will explore how plastic waste is collected and sorted in different parts of the world, and why this is a crucial step for recycling and energy conversion. Plastic waste is one of the most common and problematic types of waste in the world. It is estimated that about 300 million tons of plastic are produced every year, and only about 9% of it is recycled. The rest ends up in landfills, oceans, or incinerators, causing environmental and health problems. One of the main challenges of recycling plastic waste is to collect and sort it properly. Plastic waste comes in different shapes, sizes, colors, and types, and each type has different properties and applications. For example, PET bottles can be recycled into fibers, fabrics, or new bottles, while HDPE containers can be recycled into pipes, crates, or toys. However, if these types of plastics are mixed together, they cannot be recycled efficiently and may contaminate each other. Traditional waste collection methods rely on manual labor or simple mechanical devices to separate plastic waste from other materials. These methods are often slow, costly, inaccurate, and unsafe for workers. For example, manual sorting involves workers picking out plastic items from a conveyor belt by hand, which exposes them to dust, noise, and potential injuries. Mechanical sorting involves using magnets, screens, or air jets to separate plastic from metal, paper, or organic waste. However, these methods cannot distinguish between different types of plastics or remove contaminants such as labels, caps, or dirt. In recent years, there have been innovations in automated sorting technologies that use sensors, cameras, artificial intelligence, and robotics to identify and separate plastic waste more accurately and efficiently. These technologies can detect the shape, size, color, transparency, and chemical composition of plastic items and sort them into different categories or streams. For example, near-infrared spectroscopy, NIRS, can scan the surface of plastic items and measure the wavelength of light reflected by them. This allows the machine to determine the type of plastic and direct it to the appropriate bin or conveyor belt. Optical sorting can use cameras and software to recognize the shape and color of plastic items and sort them accordingly. For example, a machine can identify a PET bottle by its shape and a HDPE container by its color and separate them into different streams. Robotic sorting can use robotic arms with grippers or suction cups to pick up individual plastic items from a conveyor belt and place them in the designated bins or containers. The importance of efficient sorting for effective recycling and energy conversion cannot be overstated. By sorting plastic waste into homogeneous streams, recyclers can reduce the amount of contamination and increase the quality and value of the recycled products. For example, a high-quality PET stream can be recycled into food-grade bottles or packaging materials that can be used again and again. A low-quality PET stream can be recycled into lower-grade products such as carpets or clothing that have a shorter lifespan and lower value. By sorting plastic waste into different types, recyclers can also choose the most suitable recycling method for each type. For example, some types of plastics can be melted and reshaped into new products, mechanical recycling, while others can be broken down into their basic components and used to make new plastics or fuels, chemical recycling. Some types of plastics can also be converted into energy through processes such as pyrolysis or gasification. As you can see, plastic waste collection and sorting techniques are essential for reducing the environmental impact of plastic waste and creating a circular economy for plastics. By using advanced technologies such as NIAS, optical sorting, and robotic sorting, we can improve the efficiency and accuracy of sorting plastic waste and enable more effective recycling and energy conversion. Thank you for watching this video. If you liked it, please give it a thumbs up and subscribe to our channel for more videos on environmental topics. Part 4. Recycling and mechanical processing of plastic waste. In this video, we're going to talk about recycling and mechanical processing of plastic waste. Plastic waste is one of the biggest environmental problems we face today. It pollutes our oceans, harms wildlife, and contributes to climate change. But did you know that there are ways to recycle plastic waste and turn it into useful products? That's what mechanical recycling is all about. Mechanical recycling is a process that involves collecting, sorting, cleaning, shredding, and melting plastic waste to produce new plastic materials. These materials can be used to make products such as packaging, clothing, furniture, and even fuel. Mechanical recycling has many benefits, such as reducing the amount of plastic waste that ends up in landfills or incinerators, saving energy and resources, and creating jobs and economic opportunities. However, mechanical recycling also has some limitations, such as the quality degradation of recycled plastic over time, the difficulty of separating different types of plastic, and the contamination of recycled plastic by other substances. Therefore, mechanical recycling is not a perfect solution, but it is a valuable one that can help us reduce the impact of plastic waste on our planet. Mechanical recycling is a process that involves several steps to transform plastic waste into reusable materials. First, the plastic waste is collected and sorted by type and color. Then it is shredded into small pieces that are easier to handle and clean. Next, the shredded plastic is washed and rinsed to remove any dirt, labels, or other contaminants. After that, the plastic is separated by density using water or air currents, or by using infrared sensors that detect different types of plastic. Finally, the plastic is melted and extruded into pellets or flakes that can be used to make new plastic products such as bottles, containers, or fibers. Mechanical recycling has many benefits for the environment and the economy. By recycling plastic waste, we can reduce the amount of plastic that ends up in landfills or incinerators, where it can pollute the soil, water, and air. We can also save energy and resources that would otherwise be used to produce new plastic from raw materials, such as oil or natural gas. Recycling plastic can also create jobs and income for waste collectors, recyclers, and manufacturers. Mechanical recycling is one of the most common and effective ways to deal with the global problem of plastic waste. However, mechanical recycling is not a perfect solution. It has some challenges and limitations that we need to be aware of. For example, not all types of plastic can be recycled mechanically. Some plastics are too contaminated, degraded, or mixed with other materials that make them unsuitable for recycling. Also, mechanical recycling can only be done a limited number of times before the quality of the plastic deteriorates and becomes unusable. This means that mechanical recycling can only delay, but not prevent, the disposal of plastic waste. That's why we need to support and promote initiatives that aim to improve the efficiency and effectiveness of mechanical recycling. For instance, there are some projects that use advanced technologies such as optical sorting, chemical analysis, or artificial intelligence to identify and separate different types of plastic waste more accurately and quickly. There are also some initiatives that create innovative products from recycled plastic, such as furniture, clothing, or building materials. These products not only demonstrate the potential of mechanical recycling, but also raise awareness and encourage consumers to choose recycled products over new ones. I hope you learned something new. If you did, please give this video a thumbs up and subscribe to my channel for more content like this. And don't forget to share this video with your friends and family who might be interested in recycling and mechanical processing of plastic waste. Together, we can make a difference and create a more sustainable and eco-friendly world. Part 5. Chemical recycling, pyrolysis and depolymerization. In this video, we will explore two methods of chemical recycling, pyrolysis and depolymerization. We will also discuss the advantages and challenges of these methods and how they can help reduce plastic waste and create valuable products. Plastic is one of the most widely used materials in the world, but it also poses a serious environmental problem. Most plastics are not biodegradable, and they end up in landfills, oceans, and ecosystems, where they cause pollution, harm wildlife, and contribute to climate change. Recycling plastic is one way to reduce its environmental impact, but conventional mechanical recycling has its limitations. Mechanical recycling involves melting and reshaping plastic into new products, but it can only be done a few times before the plastic loses its quality and becomes unusable. Mechanical recycling also cannot handle mixed or contaminated plastics, which make up a large portion of plastic waste. This is where chemical recycling comes in. Chemical recycling is a process that breaks down plastic into its basic components, such as monomers, oligomers, or hydrocarbons, using heat, pressure, or catalysts. These components can then be used to make new plastics or other products, such as fuels, chemicals, or materials. Chemical recycling can handle a wider range of plastics than mechanical recycling, and it can produce higher quality products. Chemical recycling also has the potential to reduce greenhouse gas emissions by displacing fossil fuels as a source of raw materials. One method of chemical recycling is pyrolysis. Pyrolysis is a process that heats plastic in the absence of oxygen, causing it to decompose into gas, liquid, and solid products. The gas and liquid products can be used as fuels or feedstocks for chemical production, while the solid product, called char, can be used as a soil amendment or carbon source. Pyrolysis can convert mixed or contaminated plastics into useful products without the need for sorting or cleaning. Pyrolysis also has a high energy efficiency, as it can generate more energy than it consumes. However, pyrolysis also faces some challenges. Pyrolysis requires high temperatures and specialized equipment, which can be costly and complex to operate. Pyrolysis also produces some harmful byproducts, such as dioxins and furans, which need to be controlled and treated. Pyrolysis also depends on the market demand and price for its products, which can vary depending on the quality and composition of the feedstock and the output. Another method of chemical recycling is depolymerization. Depolymerization is a process that breaks down plastic into its original monomers or oligomers using catalysts or enzymes. These monomers or oligomers can then be used to make new plastics of the same or different types. Depolymerization can restore the quality and properties of plastic, allowing it to be recycled indefinitely. Depolymerization can also target specific types of plastics, such as polyethylene terephthalate, PT, or polylactic acid, PLA, which are widely used in packaging and textiles. However, depolymerization also has some limitations. Depolymerization requires specific conditions and catalysts or enzymes for each type of plastic, which can be expensive and difficult to obtain. Depolymerization also cannot handle mixed or contaminated plastics, which need to be separated and cleaned before the process. Depolymerization also competes with mechanical recycling for the same types of plastics, which are already easy to recycle. In conclusion, chemical recycling is an alternative way to recycle plastic that can overcome some of the challenges of mechanical recycling. Chemical recycling can convert plastic into valuable products such as fuels, chemicals, or materials, while reducing its environmental impact. However, chemical recycling also has its own challenges, such as high costs, technical difficulties, regulatory barriers, and market uncertainties. Therefore, chemical recycling needs to be integrated with other strategies, such as reducing plastic consumption, improving plastic design, enhancing mechanical recycling, and promoting circular economy principles. Part 6. Energy recovery from plastic waste incineration. In this video, we will examine the role of incineration in plastic waste management, assess the environmental impact of incineration, and explore some innovations in energy recovery systems from plastic waste incineration. One of the methods to deal with plastic waste is incineration, which is the process of burning waste at high temperatures to reduce its volume and mass, and to generate heat and electricity. Incineration can help to save landfill space, reduce greenhouse gas emissions, and provide a source of renewable energy. However, incineration also has some drawbacks, such as the emission of toxic pollutants, the loss of valuable materials, and the potential for public opposition. Therefore, it is important to evaluate the environmental impact of incineration and to adopt best practices and technologies to minimize its negative effects. Some of the factors that need to be considered are the type and composition of the waste, the efficiency and design of the incinerator, the air pollution control systems, the energy recovery and utilization, and the social and economic implications. By conducting a comprehensive assessment of these factors, it is possible to determine the optimal conditions for incineration and to ensure its sustainability and acceptability. One of the ways to improve the environmental performance of incineration is to enhance the energy recovery systems from plastic waste incineration. Energy recovery systems are devices that capture the heat or electricity generated by incineration and use it for various purposes such as heating, cooling, or powering homes and industries. By doing so, they reduce the amount of fossil fuels that need to be burned for energy production and thus lower the greenhouse gas emissions and air pollution associated with it. Moreover, they increase the efficiency and profitability of incineration plants, as they can sell the excess energy to the grid or other consumers. Energy recovery systems can be classified into two main types: thermal and electrical. Thermal energy recovery systems use the heat from incineration to produce steam, hot water, or chilled water, which can then be distributed through pipes or ducts to nearby buildings or facilities. Electrical energy recovery systems use the heat from incineration to generate electricity, either directly through a steam turbine or indirectly through a gas turbine or an internal combustion engine. The electricity can then be used on site or exported to the grid. The choice of energy recovery system depends on several factors, such as the type and quantity of waste, the local energy demand and prices, the availability of infrastructure and technology, and the environmental regulations and incentives. Some of the innovations in energy recovery systems from plastic waste incineration include gasification. This is a process that converts solid waste into a synthetic gas that can be used as a fuel for power generation or chemical production. The gasification process involves heating the waste in a low oxygen environment, which breaks down the organic molecules into hydrogen, carbon monoxide, and other gases. The synthetic gas can then be cleaned and conditioned to meet the specifications of different applications. Pyrolysis. This is a process that decomposes organic waste into a liquid oil, a solid char, and a gas that can be used as fuels or raw materials. The pyrolysis process involves heating the waste in the absence of oxygen, which causes the thermal decomposition of the organic matter. The liquid oil can be refined into diesel, gasoline, or chemicals, while the solid char can be used as a soil amendment or a carbon source. The gas can also be used as a fuel or a feedstock for chemical synthesis. Plasma arc. This is a process that uses an electric arc to create a plasma that vaporizes waste into a gas and a solid slag that can be used as construction materials. The plasma arc process involves passing an electric current through the waste, which ionizes the atoms and molecules into a plasma state. The plasma reaches temperatures of up to 10,000 degrees Celsius, which reduces the waste to its elemental components. The gas can be used to generate electricity or heat, while the slag can be vitrified into glass-like materials that are inert and stable. These innovations can help to increase the efficiency and quality of energy recovery from plastic waste incineration, as well as to reduce the emissions and residues from the process. In conclusion, incineration is a viable option for plastic waste management that can provide multiple benefits, such as waste reduction, energy generation, and greenhouse gas mitigation. However, it also has some challenges such as pollution, resource loss, and social acceptance. Therefore, it is essential to evaluate the environmental impact of incineration and to implement innovations in energy recovery systems from plastic waste. Part 7: Challenges and Environmental Concerns. Plastic to energy conversion is a promising technology that can help reduce the environmental impact of plastic waste. However, it also faces some challenges and concerns that need to be addressed before it can be widely adopted. One of the main challenges is to ensure that the emissions and byproducts from the conversion process are minimized and properly managed. Different conversion methods, such as pyrolysis, gasification, and incineration, may produce different types and amounts of pollutants, such as carbon dioxide, carbon monoxide, nitrogen oxides, sulfur oxides, dioxins, furans, and heavy metals. These pollutants can have negative effects on human health and the environment, especially if they are not captured or treated adequately. Therefore, it is important to monitor and control the emissions and byproducts from the conversion process and to comply with the relevant environmental regulations and standards. Another challenge is to analyze the carbon footprint of different plastic waste management strategies and to compare them with plastic to energy conversion. The carbon footprint is a measure of the greenhouse gas emissions associated with a product or activity throughout its life cycle. It can help evaluate the environmental impact and sustainability of different options for plastic waste management. For example, recycling plastic may have a lower carbon footprint than converting it to energy, depending on the type and quality of plastic, the recycling process, and the energy source used. However, recycling may not be feasible or cost-effective for some types of plastic waste, such as mixed or contaminated plastics. In such cases, converting them to energy may be a better alternative than landfilling or dumping them. Therefore, it is necessary to conduct a comprehensive and comparative life cycle assessment of different plastic waste management strategies and to consider the trade-offs between environmental benefits and costs. A third challenge is to address the social and ethical considerations in implementing plastic to energy technologies. These include the potential impacts on the livelihoods and well-being of the people involved in the plastic waste value chain, such as waste collectors, recyclers, and converters. For instance, converting plastic waste to energy may reduce the demand for recycled plastic materials, which may affect the income and employment opportunities of the recyclers. Moreover, implementing plastic to energy technologies may require changes in the policies and regulations governing plastic waste management, such as introducing incentives or penalties for different stakeholders. These changes may affect the rights and responsibilities of the producers, consumers, and managers of plastic waste, and may raise issues of fairness and justice. Therefore, it is essential to engage with the relevant stakeholders and communities in planning and implementing plastic to energy technologies, and to ensure that their interests and concerns are taken into account. Conclusion. In this video, we have discussed the current challenges and opportunities of plastic waste management and plastic to energy conversion technology. We have seen how plastic waste poses a serious threat to the environment and human health, and how it can be reduced, reused, recycled, or recovered through various methods. We have also explored the potential of plastic to energy conversion technology as a way to generate clean and renewable energy from plastic waste, while reducing greenhouse gas emissions in landfill space. We've learned about the different types of plastic to energy conversion processes, such as pyrolysis, gasification, and incineration, and their advantages and disadvantages. We have also examined some of the existing and emerging applications of plastic to energy conversion technology in different sectors and regions. We hope that this video has provided you with valuable information and insights on this important topic. Plastic waste management and plastic to energy conversion technology are not only technical issues, but also social, economic, and political ones. They require integrated and holistic approaches that involve multiple stakeholders and disciplines. They also demand ongoing research and innovation to overcome the technical, financial, and regulatory barriers that hinder their widespread adoption and implementation. We encourage you to continue learning and collaborating with others who share your interest and passion for finding sustainable solutions to the plastic waste problem. Together, we can make a difference for our planet and our future.